In the last lecture, we were considering the classification of systems and networks. We saw the difference between a static system and a dynamic system, the difference between a continuous time system and a discrete time system. We also observed the difference between a linear system and a nonlinear system. Basically, we said a linear system obeys the principle of superposition, that is a combination of additivity and homogeneity, and we promised ourselves at the end of the last lecture that we will look at some examples of the equations governing the performance of a linear system and a nonlinear system, and this is what we propose to do to start with. So, you recall that we said a linear system satisfies the principle of superposition if it is a continuous time system then if x1 of t as an input gives rise to an output y1 of t and x2 of t gives rise to an output y2 of t, then a linear combination of these two inputs c1 x1 of t plus c2 x2 of t for any arbitrary pair of constants c1 and c2 will give rise to an output c1 y1 of t plus c2 y2 of t. On the other hand, if we are talking about a discrete time system, naturally now the signals will not be functions of the continuous variable t, but they are functions of a discrete variable, let us say n, then the same statement will be carried over in this domain as if x1 n gives rise to an output y1 n and another arbitrary input x2 n gives rise to an output y2 n, then if the system is linear, if the discrete system is linear, then c1 times x1 n plus c2 times x2 n will give rise to a similar linear combination of the corresponding outputs. Now, the input-output relations of a continuous time linear system will be described by a differential equation, a linear differential equation, and here the corresponding equation will be called a linear difference equation. Let us look at some examples. Examples of equations pertaining to linear systems. A 4 d squared y dt squared plus 3 dy dt plus 3y is 2x plus 5 dx by dt. So, x is the input and y is the output. All the coefficients of the derivative terms are constants. So, this is certainly a linear differential equation of order 2 with constant coefficients. Therefore, this is an example of a linear, the equation corresponding to a linear continuous time system. B, y of n plus 2 plus 3y of n plus 1 plus 3yn, let us say, is 6xn. This is an example of the system equation characterizing a discrete time system which is linear. Again, the coefficients are the various output terms and the input terms are constants, and therefore, this is again a linear difference equation with constant coefficients. So, this is a characteristic of a linear discrete time system. Let us take another example, 4t dy by dt plus 2t squared y equals 6x plus 5 dx upon dt. Now, here we have the coefficients of the various derivative terms as the functions of time 2t, 2t squared and so on. This also is an equation pertaining to a linear system. One can easily manipulate these equations, find out the y1 which satisfies this for a given input x1, a y2 which satisfies this for a given input x2, and combine these two to show that if x1 of t gives rise to y1 of t, x2 of t gives rise to y2 of t, this condition is satisfied even here. In other words, if we have a linear system, it does not mean that the differential equations should have only constant coefficients. Even if the coefficients are functions of the independent variable, which is t in this case, even then it corresponds to a linear system. So, this is also an example of a linear system. A corresponding equation for a discrete time system would be something like this: n yn plus 1 plus 2 y of n equals, let us say, 5 xn plus 1 minus 6n xn. So, you see here the coefficients are not constants, but functions of n. This, at least at this, in this location, you have got n times yn plus 1. So, this corresponds to the independent variable here is t, the independent variable here is n. Therefore, if the coefficients are functions of the independent variable, still it is a linear system. It satisfies this kind of relationship, and therefore, these are examples of systems, equations which pertain to linear systems. Suppose I take a nonlinear system, then the coefficients are not necessarily constants or functions of the independent variable. The characteristic of the differential equation corresponding to a nonlinear system is that the coefficients are functions of the dependent variable y. Examples: 4y dy by dt plus 6y equals 2x plus 3x squared. So, you see that y is multiplying dy by dt, and also you have an x squared term here, and these are the two factors which destroy the linearity of this equation. Similarly, you have y squared n plus 2, suppose I have plus yn plus 1 plus 3yn equals 6x of n. Yn plus 2 is multiplied by yn plus 2. So, you can think of this, the coefficient being yn plus 2 multiplying yn plus 2. So, this is a square term that is involved here. So, this fails to be a linear difference equation. So, essentially, to summarize, what we have is, in the case of a linear system, whether it is the differential equation or the difference equation, the coefficients of the various terms, the dependent variable or its derivative or its incremented terms like this, should be either constants or functions of the independent variable t or n, as the case may be. But if the coefficients turn out to be functions of the dependent variable, then it fails to be linear. It belongs to the category of nonlinear difference or differential equations. So, we will leave it at that. The next category of the next classification that we will talk about is the difference between time invariant systems and time variable systems. So, we have the classification constant parameter versus variable parameter systems. Another name for constant parameter system is time invariant system. These two are equivalent. In other words, the parameters which characterize the system, the parameters, the various components which constitute the system, are constant with respect to time. Take the case of an electrical network. If R, L, and C are fixed in respect to time, with respect to time, it is called a constant parameter system. On the other hand, suppose you have a device in which an inductance or resistance is continuously changing with respect to time, then it becomes a time variable system. For example, if you have a carbon microphone, and depending upon the input signal that you are having, the resistance of the microphone may be changing. So that becomes a variable parameter system or a time variable system. So variable parameter system is also sometimes referred to as time variable system. Generally, we will be interested in talking about time variable system or time invariant system with respect to linear systems. That is because that is the main focus of our work. So if you look at these two equations here, or the four equations here, A and B have the derivative terms with constant coefficients, and this is characteristic of a time invariant system. Or a constant parameter system. On the other hand, in these two equations, we have coefficients, functions of time, or n as the case may be. These are time variable systems. So these describe the operations of some time variable systems. So both are linear, but these first two equations belong to the category of time invariant systems. The latter two belong to the category of time variable systems. Now, the importance of distinguishing between these two classes of systems, first of all, the solutions of these equations is much more simpler than the solutions of these equations, because the time factor t is involved here. And further, there is a very useful property of time invariant systems, which I will discuss presently, and that makes analysis of such systems far simpler than what it would be in the case of time variable systems. It goes like this. If you take a continuous time system, if you have an input, say xt, which gives rise to an output yt, then suppose this x of t is delayed by or translated in time by a certain interval, say x t minus d, then such an input will give a response which is similarly delayed in time by d units of time, no matter what t you take. For a discrete time system, you have, if x of n gives rise to an output yn, and if you consider another input signal which is the same as xn but delayed by d or k instants or n instants, n minus capital N, where n is a fixed number. So whatever is occurring at n equals 1 now is occurring at n plus 1 units, then the corresponding output will be yn. So that means the response will be shifted by the same amount, but the shape of the response will not be changing at all. Let me illustrate this by means of some figures. Suppose I have x of t, and this gives rise to a response by t like this. Then suppose I delay this signal by d units. So instead of 0, it starts here. So this is x of t minus d. then if it is a time invariant system, you are sure that the output will be the same as this, but starts a little later. This is y of t minus t. So, the same response, same wave shape, except that it is delayed by the same amount as the input is delayed. So, this is a feature of time invariant systems, and this is a very useful feature, as we will see later on when we talk about how we use impulse responses to characterize the find out the input for find out the response for general input. In the case of a discrete time system, let us say we have an xn, a signal like this, xn as a function of discrete variable n, and let us say this gives rise to a response yn like this. Of course, discrete time signals will have values only at discrete points along the time axis, and so the interval between 2 points may be any arbitrary value depending upon the system. So, let us say for integral values of n, you have certain sequence of values xn and corresponding values so yn. Now, suppose I delay this signal by n units. So, that means I starts here. So, instead of 0, it starts at n. That is your xn, otherwise it is the same. And then the corresponding y of n would be, it starts not at 0, but at point n here, and then it is as if this whole output is translated along the x axis by n units. So, that is how the response will be occurring for a shifted input signal. These particularly, as you can see, this particular property will be very useful in the case of when you want to superpose the responses due to different inputs, as we will see later. This is all for the time invariant case. In the time variable case, we cannot have this kind of property, because as you can appreciate, when this x of t is applied to the system, the parameters have certain values, and therefore there is a certain response. But if x of t has been delayed by this amount, and you are talking about the application of this at time t equals d, at this time the parameters of the system might have undergone some change. They are no longer the same values that were existing at this point. Therefore, even though the input has the same shape, the output need not follow the same shape. And that is the reason why this such property will not be valid for a time invariant system, time variable system. Time variable system, if xt gives rise to yt, then xt minus d not necessarily give rise to y of t minus d. That means it is not necessary that it is this gives rise to that particular response. So, you cannot say anything about it unless you know the actual behavior of the variables with respect to time. The next property that we will talk about, next classification of systems, is causal systems, and those which are not causal called non-causal systems. A causal system is one which is defined as follows. If you have two inputs, x1t, which gives rise to a response y1t, and x2t, which gives rise to a response y2t, and further, let us say x1t equals x2t for t less than some point t naught. That means up to some point t equals t naught, both are inputs are the same. So, you may have x1 of t up to point t naught, and afterwards maybe it goes like this, and you have another x2 which also follows the same waveform up to point t naught, but afterwards maybe deviates from the values which x1 had taken. Then if this is so, then for a causal system we can expect that y1t equals y2t for t less than t naught. So the corresponding outputs here, if y1 had some output like this up to t naught and afterwards maybe it goes like this, we can say that y2 also will have the same response maybe from here onwards. That means up to the point t naught the same input, the inputs are the same, the outputs will be the same. Such systems are said to be causal systems. Now, if this is the general definition of a causal system. In particular, for a linear causal system, if the system is not only causal but also linear, then you can easily see if I have an input which is x1 minus x2, which means up to time t naught x1 minus x2 is 0, then the output must also be 0, because superpose these two, this will also will be 0. Or we can take t naught as equal to 0 as a general case. We can say if xt is 0 for t less than 0, then the output yt is 0. That is the consequence of a linear causal system. That means the whatever input you had, if it is 0 up to this point and then this is your xt, your output must be 0 up to this point, and later on whatever output you get, you have it, but it must necessarily be 0 for t less than 0. That means before you apply the input you cannot get an output, which seems to be quite reasonable from physical arguments, and therefore we believe that all physical systems follow this causality principle. And a system which is not causal is referred to as non-causal or anticipatory systems. This is the opposite of the causal system. We believe, as I said, all physical systems that we can build follow the principle of causality. Very often one describes causality principle in these terms, but that is not quite correct in the sense, if I have a system like this and I is the response and your Vi is the input. So if Vi is the input and I is the response, even if Vi is 0, you are having a kind of current there I in that circuit. Therefore, we cannot say that this particular system follows this. If x of t is the input Vi voltage and the current I is the Yt, I will exist even if Vit is 0. Therefore, if you start a signal Vi of t from t equals 0 onwards, it does not mean that the current will be 0, because the current will be driven by the battery. But this is not a linear system. Because of the presence of the source, you do not have a proportionality relation between B and I. That is not a linear system. The resistance part is linear, but the source destroys the linearity of this. So this particular property is not valid for this. But on the other hand, this property will be valid for this system. If we have two voltages Vi1 and Vi2, they produce the same response as long as Vi1 is equal to Vi2 up to t equals t naught. So this is the more general definition of causality, and for a particular special case of a linear causal system, we can simply say if the input is 0 for time t less than 0, the output will likewise be 0 for time t less than 0. Now, another terminology that we can introduce at this stage is convenient to use such a term. Causal signal is one which is 0 for t less than 0. So, a causal signal is one which is normally defined as one which is 0 for t less than 0. That means here this x of t is a causal signal, it is 0 for t less than 0. So, one can say that the property is that if a linear causal system has a causal signal as the input, the output will also be a causal signal, right? Because when we talk about transients in linear systems and so on, it would be nice to have a term which describes all those signals which are 0 for t less than 0. They would call such signals causal signals. So, we can say a causal signal given as an input to a linear causal system will produce a response which is also a causal signal. We will have one more property classification which we will discuss. That is the number of independent variables. Systems can be classified depending upon the number of independent variables that we have to reckon with in the system. And this number of independent variables is also referred to often as the dimension of the system. So, one dimensional systems. The transients in electrical circuits are one dimensional systems because t is the independent variable. For example, t or n in the case of a discrete time system. Let us, on the other hand, think of the transients that arise in a transmission line. You have a transmission line, and therefore, at any point x, you have the voltage between these two is a function of x and the time t. So, the x is 0 from starting sending end, let us say this is x. Therefore, the voltage here depends upon two independent quantities x and t. So, along the line the voltage will change, and not only with the distance, but also with respect to time. So, you may have two dimensions. Example, transmission line where the currents and voltages are functions of x and t. Similarly, you may have a grid like structure, and you are describing some parameter here as a function of the x coordinate and y coordinate. Therefore, some quantity w which is a function of the m and n, two dimensions. These are called two dimensions, and of course, we can continue with other dimensions also. For example, if you have a field problem, electromagnetic field or electrostatic field, so it is a function of x, y, z, and perhaps if it is a dynamic, you also have a function of time. So, it may be four dimensions. And when you deal with such multidimensional problems, in the case of a continuous system, you have partial differential equations to contend with, and in the case of a discrete time system, you have a multidimensional discrete difference equations that you have to deal with. So, after having looked at the classification of the various systems, we would now like to say that as far as this course is concerned, we will be talking about linear, time invariant systems which are causal, of course, and which are one dimensional, because we are talking about only one variable at a time, t or n as the case may be. And however, we will and also dynamic, linear, time invariant, causal, one dimensional systems. This is the main focus of our course. We will also we will be talking both about continuous time systems as well as discrete time systems. Perhaps for 70% of the course material will have to do with continuous time systems, and 30% with the discrete time systems, which we will take up at the end of this course. Even though we are talking about systems in general, we will be taking specific examples from electrical networks as examples of systems, and the variables therefore will be voltages and currents, and the independent variable will be time. In the matter of analysis of dynamic systems, electrical engineers had always head start over others, because they developed powerful tools for the analysis of linear systems under various excitation patterns. The impedance concept, the phasor notation, and the early application of operational methods for dealing with dynamic systems are all due to electrical engineers. And furthermore, electrical engineers had also an access to very sophisticated experimental techniques for measurement of the various parameters under dynamic conditions, high speed recording and waveform observation, not only for verifying the results from theory, but also to gather data which will be useful to supplement the theory, with the result that the methods developed for the solution of electrical networks can be profitably employed for the solution of other class of networks as well. So we often find that systems or networks of other kinds, like mechanical systems or mechanical networks, acoustical networks or acoustical systems, hydraulic systems and so on, are sometimes modeled in terms of electrical circuits. The analogous electrical circuits for a given mechanical system is set up, and you analyze this electrical system with all the gamut or the techniques that are available for the electrical circuit analysis, and once you have that, you translate the results back to the original domain, interpret the results suitably, and then you get the solution for the non-electrical system. For experimentation also this is convenient. So instead of having to do with large masses, springs and dashpots and so on, you can set up an RLC circuit which is a replica, which simulates the actual mechanical system, and carry out all this experimentation in terms of voltage and currents, which are easy to measure in the lab, and then interpret the results suitably in the original domain. So when we study electrical networks and the dynamic performance of electrical networks in this course, we have the assurance that whatever techniques we employ and whatever methods we use here can also be profitably employed for other kinds of networks and other kinds of systems. With this, we close our discussion of the introductory remarks for this course. Next, we will take up the consideration of the different signals that we come across in our discussion of linear systems and networks. Literally, a signal is a means of conveying some information, but in the context of systems, we take the meaning of a signal to collectively indicate the various variables which describe the status of the system at any particular point in the system or at any particular point of time. As far as electrical networks are concerned, the variables or the signals that we deal with are the voltages and currents. It is the signals, as I mentioned earlier, which, so to say, give the breath of life to a system or a network, because in the absence of signals, the network or the system is completely lifeless.